Okay. Just to give a sense of understanding of people's backgrounds here, who here has heard of Fry? Pardon? Wonderful, because I'm not going to go through it today. Okay, so basically, if you think about back to 2015, 2014, and how ZK, how do you make a ZK snark? How did one construct a proof of computation? The techniques that people developed were very kind of integrated into individual protocols. You had things like Groth16, you had things like Starks, but there were no kind of general abstraction as one could apply sense of heuristics to build a modern, a ZK proving system. That has now since changed over the last several years to the point where in modern ZK you generally have three components of a modern Stark. So components. By the way, my handwriting is absolutely terrible, so I'm very sorry. I'm also left-handed, so I kind of cover up what I write with my body, so sorry about this. First of all, you have circuit arithmetization. So this is what we kind of mean when we talk about arithmetic gates. You've got some circuit with wires that feed into it, like this, and then maybe this goes into another gate, blah, 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 blah. It's a way of taking a high-level imperative computer program and converting it into an algebraic relation that you can then prove statements about. And the actual circuit arithmetization is somewhat independent of the underlying proving system. For example, take Plonk. You can build Plonk systems using an enormous bevy of proving systems, from Fry-based commitment schemes to elliptic curve-based schemes, and they all use the same arithmetization. And you have that with other schemes like CCS. But then once you have a way of converting a program to polynomial algebra, so I'll just write that out here. So converts into polynomial algebra. I'm very slow at writing. So you have from int main char pointer input into some expression over polynomials, which is equal to 0. Once you've managed to do that, then the next step is called like a polynomial interactive oracle proof. Technically, formally, you don't need to make a proving system working over polynomials, but in reality, we all do because they're easy and nice to work with. So a polynomial IOP is an interactive protocol between like a imagined prover and an imagined verifier, where the prover is sending messages to the verifier is then providing challenge responses, and this protocol either ends with the verifier accepting or rejecting the proof. And there are many ways of doing polynomial IOPs, and this is what I'm going to go to later on in the talk. So it's a way of converts some polynomial expression into a relation. So over some, we call them instance witness tuples, where the idea is so snark. By the way, I'm using snark here as a stand-in. I also mean starks. Starks are snarks. Don't let anyone tell you else otherwise. Yeah, so the idea is it's kind of some interactive protocol between a prover and a verifier. This converts the algebraic statement, which is always going to basically, if you've got some algebra which is 0, then you know the program is satisfied. It turns it into a probabilistic statement, where you have an extremely high degree of confidence that the statement, that the original program is satisfied. And by extremely high, I mean you need more computers than are on the Earth times a million or something like that. And then finally, but the polynomial IP doesn't. It's not the final step. It's not the final step. What happens here is it's reducing the algebra into it's reducing algebra over polynomials into algebra over generally elements of prime fields. So the idea is you can have these polynomials with millions, billions of coefficients inside of them, representing large circuits, and the polynomial interactive oracle proof will compress this all down into some statement involving individual field elements. And then you have a polynomial commitment scheme. So the idea is that the IOP the IOP will result in basically a claim saying, I have these commitments to these polynomials, and if these polynomials evaluate to certain values produced by this IOP, then the proof is true. So what do I mean by a commitment scheme? So I'm going to go up here now, PCS. So the idea is, it's a way of efficiently. What do we first mean by commitment? So what is a cryptographic commitment? So imagine you have some X, which is a commitment to. No, I use X too much. I don't know. F is a commitment to P of X. This is basically saying I've got some polynomial. I'm going to create a cryptographic commitment. So some small piece of information which represents a polynomial, and it has the properties of it has to be binding. The idea is that F will not be equal to some other polynomial if P prime is not P. So the idea is that so we use elliptic curve commitments in Aztec. I didn't say who I was, by the way. I'm Zach. I'm the CEO of Aztec. We do privacy. So the idea is we commit to polynomials using elliptic curve points, where eventually you can have some very high degree lobby polynomial. You compress it down to a single elliptic curve point, 64 bytes of data, and that kind of uniquely defines the polynomial. You can prove that you will need to break some extremely difficult cryptographic problems in order to provide a commitment to a different polynomial where the elliptic curve points match. And sometimes they're also hiding. So hiding is basically this is like a massive oversimplification, but that the commitment looks random. So it leaks no information. So the idea is that if I give you a valid polynomial commitment, it just looks like a random. It's uniformly randomly distributed across some domain. So for us, it'll be elliptic curve points. And so the idea of the commitment scheme is enables a prover to commit to some polynomial P of X, and then at some later point prove that say Z is P of alpha, where like Z and alpha are in some prime field. So the idea here is that what we use them for is, in the polynomial IP, the way we reduce down tests over polynomials into tests over points is by using effectively what you'll end up with is verify saying, all right, here's some random values. Evaluate your polynomials at these values, and I expect them to equal other specific values that you've given me. And then the commitment scheme is a way of doing that efficiently and succinctly. And so you can combine all these to acquire the properties of succinctness. So the actual proof size will be very, very small relative to the size of your program. And you have often zero knowledge, where the idea is you can hide information within your program. It can be encrypted, and the proof leaks no information. It just looks uniformly random. So why am I talking about these building blocks? Well, this is all like relatively canonical these days, but it was quite radical, say, back in 2019 when Ariel and I were putting together Plonk. You started to see these concepts starting to emerge within the literature by that point, particularly papers by Jens Groth and Jonathan Bootle, but it hadn't really been formalized. And these abstractions allow you to, it massively expands the design space of creating program ZK circuits, ZK proving systems, because you can get a level of kind of composability between different proving systems. So for example, Aztec uses elliptic curve-based cryptography because we have specific needs that elliptic curves are very well suited for, but other protocols like Polygon, Mydon, they'll use Starks because they have their properties that Starks need, but we could all use the same circuit automatizations. We can all use the same techniques and tooling and share information, and it just enables the space to grow and expand a lot more. And what's happened is there's been an enormous amount of divergence here. So this is the focus of the design of research. Like, not all of it, but a lot of it is at the polynomial IP level. And I want to go into a little bit about how the space is evolving, particularly because what we're seeing is, of all the projects using ZK, they all have radically different requirements. For example, imagine you're building a scaling layer 2. So you want to be able to compute proofs of Ethereum blocks very cheaply, very efficiently, so you can then just post the block proof on chain instead of all the transactions. You don't care about zero knowledge, which means you don't care about privacy, which means that you're very comfortable having some relatively centralized, computationally well-resourced third party to make your proofs, so like a giant cluster of server farm on AWS, for example. Whereas, take Aztec, we care about privacy. Our zero-knowledge proofs need to be computed locally by individual users on commodity hardware. So we care about very different things. We care about very efficient proof constructions, but we also care about things like very low memory consumption. We can't throw half a terabyte of RAM at the problem. And we're willing to make other trade-offs for those properties. And so, and this is, you can talk to every single protocol, and they will all have slightly different design requirements, which means that they're going to slightly be tweaking this layer to maximize performance for their specific needs. So I do think it can be a little bit misleading when some people will there's lots of claims flying around about what's the best proving system. I don't think that there really is a best proving system right now. There's going to be a best proving system for a specific application, but the way I see it, we're not like where computing was in the 1960s, where if you have a project that needs to perform a lot of compute, like, I don't know, radar research or trying to send rockets to the moon, you're going to build your own hardware, and you can optimize your own hardware, and the actual circuits directly for your particular use case, because the tech is just a little bit too primitive to be completely general purpose. That's going to take a few more years. So this is where I want to go into how do Starks and Snarks differ at the polynomial IOP level. So just going to rub this one off. So main IOP camps. There are two kinds. There are ones based around, IOP piece polynomial commitment schemes. There's actually, sorry, I'm editing this a bit. I'm going to slightly rewind what I said before. I'm not sure it's really diverging the IOP. What's happening is people are fixing polynomial commitment schemes to their needs, and then that influences the design of their IOPs. So you basically you have two camps. One, elliptic curve-based commitments. Where you have some commitment to some polynomial, which is going to be the sum of there's loads of ways of doing it, but some coefficients times an elliptic curve point that represents x to the I, where x is some trusted setup parameter. Might not necessarily be trusted setup. I'm oversimplifying, but basically the idea is your polynomial commitment becomes an elliptic curve point, and then you have hash-based commitments schemes, where the idea is you have a Merkle tree where you have your polynomial coefficients as leaves, more or less, and then this is the Merkle root of our hash tree. And the idea is this root becomes your succinct commitment. So they're doing the same thing. You're committing to polynomials, but the way that you're doing it is radically different. Has very different security assumptions as well. And they have very distinct benefits and trade-offs. So why would people use one over the other? Well, let's start with elliptic curves. So they are, it's going to be, you have to use roughly 256-bit prime fields here, because if you want to target the 128-bit security parameter, you've got to use the 256-bit elliptic curve. Therefore, you're working over 256 prime fields. Congratulations. They are homomorphically additive. This is going to be important later. So the idea is that if you have P1 plus P2, this is equivalent to adding the polynomials together before committing to them. And this is very powerful. It allows for increases the design space of the protocols that can use polynomial commitment schemes, because you can add, your verifier can combine polynomials, add them together, create random linear combinations in a way that you can't efficiently do with hash-based schemes. And the very small proof sizes. So you have, I think gross 16 is 256 bytes, and it goes up to a few kilobytes. Now, hash-based schemes. By the way, I have my own biases here because I use elliptic curves, so take all this with a grain of salt. So hash-based schemes, they can use 32-bit prime fields. So the value of hash-based commitment schemes is what you're committing to here can be tiny. You can commit to tiny polynomials, and you can acquire your the security of your proving system by when you're performing the Fry-based like membership proofs, etc., and your your distance checks. You can work over a extension field of your prime field. So the idea is you have some 32-bit field, but you work over a size 8 extension field, so f to the 8, and voila, you have 256 bits of security. And that means that witness computation is extremely efficient. Generally, constructing your proof is going to be a heck of a lot faster over 32-bit prime fields because the cost of prime field operations, well, multiplications, are roughly order n squared, where n is the log of your field size. It's like the number of bits. This is a massive oversimplification. It's actually generally 256-bit fields will be between about 32 times slower to work with, or maybe 16 if you're lucky, but that's a big difference. So why would anybody use elliptic curves if your proof construction is 16 times faster? Well, there's two downsides to this. One is they're not homomorphically additive, so no linear isomorphisms you can apply because there's you can't add Merkle hashes together, and also the relatively large proof sizes. So roughly about I think it's 32K to probably a meg if you want to go a bit crazy. So that's at a high level the differences. Practically, what does that mean? So here's how I view the trade-off space between them. Blip.
Is there any other hash-based commitment scheme apart from Rai?
There's tons in the literature, but I don't know of any that are actually being used or built because generally the constants are not very good. I do know that there's, I think one very interesting area of research is linear time hash-based commitment schemes. So ones where, because at the moment with Fry, the complexity is n log n if you want to commit to a degree n polynomial, open one. And in theory, in the literature, there are commitment schemes where the opening proof is just linear in the size of your polynomial, but the constants are really, really bad. And the proof sizes are absolutely ginormous, so they're not really used. But it's an active area of research. And yeah, if I was just getting into the space and I wanted to do research, that's where I'd look. Yeah, so high-level trade-offs. For ECC, actually, let's do a table. Let's make a table. A very wiggly, squiggly table. So we have ECC, we have, no, hang on, sorry. ECC, we have hashes. Boop. And we're going to say, let's say, cost per gate. Cost of recursion. Memory consumption. There are many other parameters one can measure, but at least for our sake, these are the ones that generally seem to be the most relevant, because proof size doesn't really matter that much if you use recursion. The idea is that, say you have some stonking great big proof and you want to post a very small proof on chain. Well, you use a proof, you use the fastest proof system you can to make these giant fat proofs, and then you use a much slower proving system to just verify that single proof, compress it down, and generally that works. It doesn't actually work in one of our use cases I'll go into a bit, but generally it's a good approach. So cost per gate, ECC loses one, hash wins by a walking mile. Cost of recursion, we haven't quite seen this in implementations yet because implementations are lagging research, but if you want to kind of verify a proof of correctness inside another proof, elliptic curves are amazing. If you combine the latest folding schemes with techniques like Goblin Plonk, or there was the Strinath who did Hypernova, there was something he did a later paper about that helps with the recursion, but I can't remember the name of it. Cycle Nova? So use those techniques. Cycle fold. You can get some very, very efficient recursion costs. And the memory consumption, this again, elliptic curves are very good at this now because we have linear time schemes for elliptic curves. The idea is, if you have some proof you're making, the proof complexity is literally ON. Well, why is that important? It's because imagine over elliptic curves, you're working over large fields, but imagine you have like a column in your execution trace or like a polynomial where the witness values are all small. So it's like a selector that's 0 or 1, or it represents a 16 or 32-bit register. With modern ECC-based schemes, the values, when you're constructing proofs of correctness, the values of those polynomials stay small, and they stay small in memory, which means you can represent, each word can be 32 bits. With Fry and hash-based schemes, because you have to perform fast Fourier transforms to sample your polynomials over extended domains. First of all, that will blow up the proof size by at least a factor of 2 because you're doing an FFT, but also it destroys the structure of your witnesses. As in, if you have a polynomial where all the witness values are small, once you apply a fast Fourier transform to get the evaluations over extended domain, they're not small anymore. So it means that, and because at that point you have to use extension fields, it means that each kind of wire in your circuit is going to basically be roughly 32 bytes of RAM. This is why, for example, like the Polygon ZKVM, amazing technical feat, it uses half a terabyte of RAM. So basically, the way I see it, the conclusion is relatively straightforward. If you want to use ZK for privacy, so you're making proofs locally, typically you're probably going to be your users are going to be interacting in a web browser. If you're building some kind of like generic infrastructure, they're going to be making proofs in a web browser. And there are plenty of phones where the OS will just nuke any tab that uses more than a gigabyte of RAM. So this is actually the defining consideration. And if memory consumption is a defining consideration, that also means recursion is a defining consideration, because how do you take a complex computation and make a ZK proof of it without using a lot of memory? Well, you split it up into little chunks, miniature circuits, and then you compose them all together via recursion. But if you don't care about ZK, you just care about scaling, you want to do something like RISC-0, you want to do something like Starkware, then use hash-based schemes, because you don't care about, you can recurse with hash-based schemes. It's not efficient, but as long as the amount of work you're doing in your computation circuit is much larger than the amount of work you're doing when you're recursing, you're fine. And similarly, you don't really care about memory consumption if you're renting giant server farms. So basically, where I see it, this is good for privacy. And this is good for scaling. But yeah, basically we're seeing a big divergence because a lot of the designs that use hash, typically the designs for hash-based schemes can be applied to curve-based schemes, but it might not be very efficient. Whereas you can't really go the other way, because folding schemes require the verifier to create random combinations of polynomials, and if you can't just literally add elliptic curve points together, then that becomes very, very expensive in the hash-based scheme, so you lose all the advantages. Anyway, so yeah, that's my overview of the landscape. Yeah, thanks for coming to my TED talk.
So with hash-based schemes, you can still recurse, but as you don't have additive homomorphism, you cannot do folding, for instance,
Yeah.
so it's less efficient.
Exactly. So if you wind back 2, 3, 4 years, the consensus was actually the complete opposite, because if you want to recurse over elliptic curves, you need to do this. You need to do this, well, I don't know if there's a formal name for it. I call it curve bouncing, because the idea is if you have some, let's say you define some elliptic curve group G in FP squared, then the order of your group is going to be, let's say it's R. And let's just assume R is prime. Sometimes it's not, but if you want to recurse it, it's going to be. So the idea is P, R prime. They're very close to each other. They're very similar. There's like a proof called the Hasselbalch, which basically says that the difference between P and R, this delta is less than the square root of P. So these are, but they're not the same. And this is a big problem, because when you're making a circuit using elliptic curves, all your circuit arithmetic is going to be modulo R. Now, what happens if you're building a circuit and you want to verify a proof made over the same elliptic curve. Well, now you need to do arithmetic modulo P in a circuit where you add model operations and modulo R. That's a pain in the neck. And there are techniques to get to do that. There's Halo, there's Gobblplonk, and and other things. But it's annoying. And so this is the reason why, for example, when we released Esther Connect in 2020, we had recursion, but it was basically the dumb brute force way, where we were literally running a verify algorithm inside a snark circuit, just brute forcing this non-native field arithmetic, and it cost us like 800,000 constraints. Whereas with modern techniques, you can probably get that down to about 8,000. So back in the day, people thought, Starks are the way you recurse, because in a Stark, everything's over the same prime field, so you're golden. But with the advent of folding, and we've got very, very advanced techniques now, which remove effectively the difficulty of performing this curve bouncing. Things have changed the other way now, where the elliptic curve-based schemes, they're much faster to recurse over with hash-based schemes, because with hash-based schemes, you basically have to recurse, you have to run the full verify algorithm in a circuit and evaluate it. Whereas with elliptic curves, you can basically cheat. That's the way I see it. Yep.
Are there any ongoing research around building these Merkle trees for these hash-based schemes using some hash mechanism that's additively homomorphic?
No, not that I'm aware of. I mean, there might be some early stage research, but at least not within like the community of Web3 cryptographers, because, well, we don't really know of a way of doing it that's efficient. One of the problems with trying to create a homomorphic hash function is that if you have some kind of homomorphism, then by definition you're preserving some kind of structure of your pre-image. And one of the key critical properties of a hash function is that they can be treated as a random oracle. And by that I mean that if I give you a hash of something, that hash looks uniformly randomly distributed to you. And you can't extract any information from it. Now that's not true of schemes that have homomorphism. So take a elliptic curve. So have you heard of something called a Pedersen hash? Yeah. So Pedersen hash, that's kind of a fake name. Like we use Pedersen hashes a lot, but a Pedersen hash it's collision resistant. Where the idea is that if I hash x and I hash y, then the chances of this producing the same output is rare. Like you have to solve the discrete logarithm problem if you do that, which breaks most of modern crypto. All of the web is secure with elliptic curves in modern finance. So yeah, have fun with that. But the problem there is that the hash output needs to be a field element. The idea is your inputs are field elements, your output needs to be a field element. And that field element's not going to be uniformly randomly distributed within the field, because generally the way you do a Pedersen hash is you take x, you multiply x by some elliptic curve point g, and you take the x coordinate. And that x coordinate is going to have some bias to it, because your elliptic curve point that you produce might be uniformly randomly distributed across the set of elliptic curve points, but that does not mean that the x and y coordinates will be uniformly randomly distributed across the field, which means there's a bias there. So in practice, in real terms, maybe it could be okay to use Pedersen hashes somewhere you need random oracles, but there's no formal security proofs. So to actually do that in practice would be extremely reckless.
Yeah, hashes are in general destroy the structure.
Yeah.
The substructure.
Yeah. See, the only way to get homomorphisms with a hash-based scheme is to weaken the definition of hash function, and then prove that weakened definition works for you.
Do folding schemes change this trade-off more? Like, can folding schemes result in this cost per gate of the proving system being less than that for a hash-based scheme?
No. So I'm thinking about folding schemes in here. So folding schemes don't change the cost per gate. Folding schemes, well, actually, okay, they kind of do a little bit. But even with folding schemes, your fundamental problem is that all your arithmetic is over 256-bit prime fields. And with hash-based scheme, it's over 32-bit prime fields. Now, with folding schemes, you can get away with doing less arithmetic in some cases. But so some people will claim that benefit will make them faster than the hashes. I guess, okay. Let me clarify this a little bit. The cost per gate for elliptic curve schemes is always going to be way worse than hashes, but the amount of work you can do per gate is going to be better for ECC schemes, because you can use things like giant pre-computed lookup tables through CQ. But it's still kind of a little bit ambiguous in my head whether that's going to give concretely faster proving numbers. Certainly there are people that think they will. Justin Taylor, who produced Lasso and Jolt, them and the ACC team are quite busy building out like a full VM using Lasso, and I'm very curious about the numbers because I want them to succeed. I want them to be faster than Stux, but I'm not sure they will be. But we'll see.
And I've also seen some numbers like flying around where someone claimed that in SHA-256, like a number of SHA-256 hash rates proved using Nova was similar to like the proving time that Stuxy took.
Yeah.
Like I'm not sure how to.
Maybe, but okay. I'm a little bit jaded when it comes to benchmarks. Like, I think all benchmarks are juiced. They're more juiced than like people running the Tour de France. And then by that I mean, if you want to imagine you've got a paper with a cool protocol and you want to prove that protocols are faster, so you're going to have some fancy table which describes your performance and it's going to be better than everything else. And I know this because I've done it with Plonk. But there's a big difference between general purpose proofs of computation and proofs of computation of very specific algorithms. Let's give SHA-256 for example. Now Nova's benchmarks SHA-256 are very, very good, and they're legitimate benchmarks, right? You can see the repos. It's a circuit. It proves SHA-256. It's not lying. There's a but though. If you think about the breakdown of a SHA-256 circuit, Nova uses ARM on CS, and SHA-256 is a bitwise hash function, which means that every single witness in that circuit is going to be 1 or it's going to be 0. Now, that means committing to the witness is going to be very, very cheap because every single witness, instead of it being an elliptic curve scalar multiplication for over a prime field, it's an addition, or maybe no addition at all if the value is a 0. So for the case of SHA-256, Nova is very, very competitive with hash-based functions. You change that hash function to Poseidon, it doesn't look the same. So if you change it to any Stark or Stark-friendly hash function, then that performance advantage gets deteriorated greatly because the witnesses are now full prime field elements.
Yeah, another question. What do you think about the lattice-based Snark? Because in the lattice community, they have many different, actively homomorphic polynomial communities and something like that. But proof size kind of large. But I think probably, we in the near future we can have more efficient lattice-based schemes.
I think lattice-based schemes are really interesting. I do think that right now it seems like the lattice crypto community and the Web3 crypto community, and by crypto I mean cryptographers, don't really talk that much. And
Jonathan Butto and
yeah.
they have a paper last year.
It's starting to change because people are noticing that, wow, lattice-based schemes are really fast, and we're in a domain where there are tricks you could use to shrink the proof size if you care about proof size. My own domain knowledge is pretty limited. If I had the ability to take a sabbatical, I think there's two things I'd study up on: lattice-based crypto and fully homomorphic encryption. But I'm a bit of an old timer when it comes to crypto, so I'm not really the best person to talk about lattices. Other than I think that there's a good chance that they'll be a big part of the future ZK mix. Cool. Well, thank you very much.